Last time we were solving the delta function potential, the delta well potential, and we had solved for the one bound state, and then we began work on solving for the scattering states for the delta function potential. And we came all the way over to this point where we were matching the two solutions, x greater than 0, x less than 0, at, I should say the derivatives of those solutions at x equals 0. And we found these two expressions, d psi dx from the negative direction, d psi dx from the positive direction. What I'd like to do then is let's continue on and make our way toward finding the scattering states. In this case, we're going to define, well, let me write it this way first. We'll write what we had before, delta of d psi dx is equal to I k f minus g minus a plus b. And psi of 0 is equal to a plus b. Therefore, I k f minus g minus a plus b is equal to 2m alpha over h bar squared times a plus b. I'm going to define beta equal to m alpha divided by h bar squared k. That means f minus g is equal to a times 1 plus 2i beta minus b times 1 minus 2i beta. If we combine that with the equation a plus b is equal to f plus g, you have 2, I'll write that down here, a plus b is equal to f plus g, from where we match the solutions at 0. We're going to have 2 equations and 5 unknowns. Okay, that sounds like a problem. What we have to do then is examine the solutions a little bit more carefully. So let's just say we have a particle that's incident from the left. If this is the case, the amplitude of the wave coming in from the right should be 0, since the particle is infinite from the left. So that's the case. G is going to be 0. That'll get rid of 1. That means A would be the amplitude of the incident wave. B would be the amplitude of the reflected wave. And F would be the amplitude of the scattered wave. Or the transmitted wave, if you like. So we can solve the previous equations in terms of one variable. So we'll solve for B and F, so we can find an amplitude for reflection and amplitude for transmission or scattering in terms of the incident amplitude A. If we do that, very simple algebra, B becomes equal to I beta divided by 1 minus I beta times A. F is equal to 1 over 1 minus I beta times A. So that's the amplitude for the reflected wave, the amplitude for the transmitted wave, or the scattered wave. The relative probability for reflection is just the reflection amplitude squared. And we can define that, or let's do it this way. We're going to define our reflection coefficient as the amplitude of the reflected wave squared divided by the amplitude of the incident wave squared. By the same token, we are going to define our probability of transmission as the amplitude of the scattered wave or transmitted wave squared divided by the amplitude of the incident wave squared. And of course it must be, it's either reflected or transmitted. So if I add the two coefficients together, of course I should get 1. If I do this and a bit of algebra, I'll find that my transmission coefficient is going to be 1 plus m alpha squared divided by 2 h bar squared e. And my reflection coefficient is going to be equal to 1 divided by 1 plus quantity 2h bar e, h bar squared e divided by m alpha squared. So that is my transmission and reflection coefficient. By the way, you can check it. You add the two together, you should get 1. As notice as the energy gets larger, we see that the transmission coefficient should get larger and larger, and the reflection coefficient should get smaller and smaller, which is physical. That's what we would expect. Now, the wave functions that we would have gotten from the scattered part can't be normalized. That's one of the characteristics of scattering wave functions. So they can't represent physical particle states. What we can do, though, is form normalizable linear combinations of the stationary states, like we did for the free particle, and the wave packets that result from this will represent physical particles. You need a computer to do this, though. We're not going to try that. Just a wrinkle on this. The problem that we've just solved was a delta function potential. So, sort of a coarse drawing of that, since I can't really draw a delta function, would be something like this. On the other hand, you could also do it for a delta function barrier. So something that looks approximately like this. It's similar to, so instead of a minus alpha delta x here, we would make this a plus alpha delta x for this potential. And it will be fairly similar, although the results will be that there are no bound states in this case. The reflection and transmission coefficients would be exactly the same as before because they both depend upon alpha squared, and whether it's minus alpha or plus alpha, you're going to get the same number. What that says is that the particle is as likely to pass through the barrier as it is to cross over the delta function well. That's distinctly non-classical. One would not expect a particle to jump over an infinitely high barrier. That doesn't seem to, that makes no physical sense to us. Quantum mechanically, of course, what we mean by that is the particle is said to tunnel through the potential. It's got a lot of, tunneling is not a figment of our imagination or just an artifact of mathematics. Tunneling is an actual effect. You see it in tunnel diodes and electronics. You see it in a number of other things, a number of other physics applications. Conversely, even if the energy is greater than the maximum potential, there's a finite probability that the particle will reflect from it, which again is distinctly non-classical, yet can happen in quantum mechanics. So that culminates our treatment of the delta function well and delta function barrier, and the result being that you can get both bound and scattering states, at least in the case with the delta function well. Next time, what I'd like to cover is the finite square well, which is another very, very interesting but somewhat complicated problem in one-dimensional Schrodinger equation. We'll do that next